All right. So today I'm going to be explaining a different paper, and this is a new playlist, denoising score matching. The score matching started in 2005 by the very famous paper of Havarianen. He's Finnish, and in 2005. Now this paper is in 2011, I think 2011, and it is based on this paper, 2005. So these methods are important because even in diffusion, the STE-based approach, the reverse one, needs to know a learned score function, score matching. So that's why it is also useful for diffusion, but by its own, it builds the foundation because there are two paradigms. Let's say there are explicit methods that are want to maximize the likelihood, but it's very hard, like energy function, it's very hard to do it explicitly. That's why we approximate it with elbow. But these explicit methods, even the elbow loss, still has many problems because it's just a lower bound we want to maximize. So there is another approach. Instead of dealing with P directly, we deal with gradient of P, and this is the approach of the score matching. And denoising score matching, they notice that because the data lies in a low dimensional manifold, so if you just put noise, then you can do it. But of course, it has many problems as well. So this paper in 2011, which is communicated by Havarianen as well, written by Pascal Vincent. So denoising autoencoders have been previously shown to be competitive alternative to restrictive Boltzmann machine for unsupervised pre-training of each layer of a deep architecture. We show that a simple denoising autoencoder training criterion is equivalent to matching the score with respect to the data of a specific energy-based model, that of non-parametric Poisson density. Also, if you look at so another interesting connection between score matching is score matching can be written as it's related to flow matching as well, because in flow matching the reverse one is not, there is no stochasticity, there is no noise, everything is deterministic. But the vector field, in the vector field you see a term S, which is the score matching. You can write it to show that it, so it is connected to many interesting paradigms in generative models. So this is the terminology that they use in this paper. So Q0 is the empirical PDF associated with DN. And of course, even in 2005, they noticed that it is equivalent to the denoising autoencoder and the explicit approach. So here, the score matching, explicit score matching. First, as I said, it is introduced in 2005. But in energy-based methods, the denominator is not tractable. So explicit methods does not work. That's why they invented score matching in 2005. And here, this is the corresponding objective function to be minimized. So this is the squared error between these two vectors. Because we don't know the true distribution, so we need to rewrite it in this way, which is just a property of this. You can rewrite it easily like this. And this line is very important because now you don't need to wonder how to calculate. Everything is based on score of X. You can learn it because your expectation is you draw from Q of X. And this is the finite sample version of implicit score matching, because your expectation can be substituted by this empirical approximation. And so they showed that this explicit score matching is equivalent to implicit score matching. and at infinity, n goes to infinity, they are equivalent. So this is the link between score matching and denoising autoencoder objective. You know, in autoencoder, if you don't put the noisy version, then it's just a reverse thing. It's not an interesting thing. But if you put the noisy signal into that, which is a denoising autoencoder, it is very interesting. If you look at the loss and training, it's very equivalent to what we do in score matching, denoising and score matching. So they are completely equivalent, and that's why they prove that they are equivalent. So an energy function that yields a denoising autoencoder objective. So we can choose the model P. We don't do it explicitly in the score matching, but here I want to show how it is related to the denoising autoencoder, because if you just take this particular kind of probability, which is based on the energy, but e to the minus e to the exponential of minus energy, then if you work on this, if you just substitute this energy, you will see that take the gradient, then it becomes this. And finally, if you here simplify it, you can rewrite it as a single equation. And then substitute again we get for this choice of Part1 kernel and density model, we can show that this denoising score matching objective is equivalent to denoising autoencoder. You see, it's just reconstructing the same thing. So this is very important that all of these methods are equivalent. So the explicit score matching criterion using the Part1 density estimator can be written. They showed it in appendix that we can develop it like this. Here is S is here, and this is the expectation of norm of psi. So it's very simple. If you look at these equations, you can see how they are equivalent.